My name's Eric Horschman, and I'm joined by Jeff Bowles of Tenaja Group, and we're going to talk about some of the findings of a project that we've recently completed, which is an update on comparing VM density that you can achieve on various hypervisor platforms. And Jeff is going to take the second part of the presentation and present the findings of our latest round of that testing that Tenaja Group has conducted with us, and show you how ESX, which is part of vSphere, compares to the latest competitive hypervisors from Microsoft, Hyper-V R2, Citrix Zen Server 5.6, and Red Hat Enterprise Linux 5.5 KVM. So Jeff's got some very interesting numbers coming up. I want to first take you through, after our disclaimer here, a rundown of why we feel VM density is an important metric to be tracking in your virtualization deployments. And then go over some of the features that are important to look for in hypervisors that contribute to good VM density. And then Jeff's going to go into the findings from our head-to-head comparison testing. So VM density is simply how many VMs can you run on a given hardware platform. And you can measure it in terms of VMs per core, VMs per socket, per server, per cluster of hosts, and for an entire cloud. And if I put up my points there. Now, VM density will benefit you cost-wise. The more VMs you can run on a given set of hardware platforms, the less you've got to pay for those servers, for their installed memory, network, and storage adapters, the less data center floor space you have to maintain for your virtual infrastructure. It's a whole cascade of cost benefits that fall out of achieving better VM density. And then there are also operational cost benefits. You've got fewer machines to manage. You can get by with a better admin to server ratio, take more advantage of the automation provided with virtualization products to lower operational expenses with the flexibility and ease of use of virtualization. And VMware has been publishing for some time now a calculator on our website. We call it our cost per application calculator. And this will take as inputs the number of virtual machines you need to run, and we equate applications to virtual machines because most of our customers run one application per VM, similar to what they do on physical machines. And this cost per application calculator will let you compare the cost of supporting that number of virtual machines on VMware vSphere, various editions, compared to other hypervisors. And an important assumption built into this cost per application calculator is the VM density that you can achieve on these platforms. And we've found through use of this calculator and some very careful cost buildups that it includes that even a slight VM density advantage has a tremendous effect on lowering the total cost of ownership for a virtual infrastructure. And we allow the cost per application calculator to let you vary that VM density. We've got some sensitivity analyses built into the output of the calculator. But a typical example shown here would be the cost to support 100 virtual machines, and we're going to compare vSphere Enterprise Plus, our bundle that includes all the vSphere features, together with vCenter, to Microsoft Hyper-V R2 and the System Center components that are needed to provide equivalent functionality to what you get with vSphere and vCenter. And the cost per application calculator has some key assumptions in it. The VM density expressed in consolidation ratio. We're showing a difference here, 18-to-1 for vSphere, 12-to-1 for Hyper-V. And this, it turns out, has a very critical impact on the results of this cost calculation. And you may be asking, why are we assuming a better VM density with vSphere? And Jeff's results from the testing conducted with Tenaja Group will show you why we feel that this is a very comfortably achievable margin in VM density over the competing hypervisor products out there. The cost per application calculator will build up the cost starting with server hardware, and that includes not just the hosts for your hypervisors, but also the management servers that you need to manage this infrastructure. The storage costs, networking, power, space, these licenses for the guest operating systems. We're assuming an all Windows infrastructure here. the licenses for the virtualization software, in the case of vSphere for VMware, the management component costs, that would be vCenter, and adding that up with this 100 VM example where we're able to achieve a better VM density with vSphere, we've got a 12% lower cost for our Enterprise Plus product. This is our product that has all the bells and whistles, coming in at lower costs than a Microsoft product. When Microsoft is telling customers that their approach to virtualization is going to cost from 1/3 to 1/6 as much. And we found it's just not accurate when you include all the associated costs, especially all the management components that a Microsoft solution requires. As more hosts are needed to support a given number of VMs with Hyper-V and other competing hypervisors, they also need more management servers. That results in more hardware, more database licenses, and so on. So cost per application is clearly very important in getting an accurate picture of what it's going to take to deploy a virtual infrastructure. Now, VM density is going through some real changes driven by hardware advancements that are occurring at a pretty rapid pace. First of all, processor cores are becoming cheaper and cheaper. Intel and AMD are now delivering 8 and 12 core processors for server systems, and their roadmaps show that number of cores per socket doubling by about 2014. That's going to mean that a 64-core server is going to be your mainstream blade or 2U rack server very shortly. So you've got to prepare yourself for using up that compute capacity that Intel and AMD are going to be delivering. Virtualization, of course, is the ideal way to do that. Memory, which has usually been the limiting factor for VM density, you'll usually run out of memory first before any other resource, has also been dropping due to Moore's Law's progress. And we're expecting, based on roadmaps from our hardware partners, that you'll be able to get a 16 gig DIMM in 2013 for what a 2 gig DIMM costs now. So most of our customers tell us that they stay away from high memory densities because those high-capacity DIMMs are just so expensive. That's changing very rapidly. The capacity of servers is also going up, so the number of memory sockets and the bus capacity is being increased to support those higher memory densities. That's going to drive up VM density. So a 0.5 terabyte server is going to cost you about the same in a few years as what you're paying now for a 64 gig server. So memory, which has been a limiting factor for a lot of customers, is rapidly fading away as a bottleneck for VM density. And then network ports, which sometimes you run out of if you've got a very network-intensive set of virtual machines and you need a lot of gigabit network ports. You might run out of network ports on a server or a blade. 10 gig networking is going to start relaxing that constraint with the adoption of mixing of storage and network traffic across 10 gig pathways, cheaper 10 gig network ports. So the result is that hardware is going to be going away as a limiting factor for VM densities. It's more and more going to be the ability of your virtualization platform to support high VM densities and allow you to manage those high VM densities effectively. That's going to be what you need to look for to take advantage of all this hardware power that's being delivered. Now, trends in VM density are showing that it's clearly increasing over time. These are numbers from IDC showing shipments of host machines, physical machines, and then virtual machines shown by the green bars. So in any one year, if we divide the green bar by the yellow bar here, that gives us the VM density out in the marketplace. And this IDC survey shows that VM densities are tripling over this 2005 to 2013 period. And this is across all virtualization technologies and all compute platforms, x86, mainframes, Unix systems, and so on. So this 8.4 VM density they're forecasting for 2013 is actually at the low end based on numbers from some other analysts that have been looking at larger customers. This is a survey from the Gartner 2009 Data Center Conference, which is typically attended by larger enterprises. These survey respondents are showing that they commonly run at 20 virtual machines per server and higher. Higher numbers than what we showed in that IDC survey. And this matches up with what VMware has seen from our own polling of our customer base. Customers are getting up to very high levels of VM density with the current generation of software and servers. The typical trend that a customer follows in VM density that we've seen by monitoring across our installed base of users looks like this, where VM density is going to start increasing initially as the customer rolls out virtualization used for server consolidation on dev test and lightweight servers. They get more confident in it. They start packing more VMs onto a host. But then as they start tackling their heavier workloads, their tier 1 server applications, we see VM density trending down for a period. This is because they have bigger workloads to put on their host machines. In some cases, customers will even go all the way down to 1 VM per server for especially large workloads, but they want to take advantage of the ease of administration from virtualization. But then we see the virtual machine density trending back up again as the customers start taking advantage of features in vSphere like DRS, resource pools, things that let them drive up VM density, and also standardizing on higher capacity machines configured with more memory, more network ports, more processor cores to support virtualization. So this is very consistent, this S-shaped curve across our entire customer base, and you may be going through some of the same sequence yourself. When we asked customers at VMworld last year what was preventing them from achieving high VM density, the most common answer was, I'm simply out of hardware capacity. Usually they've run out of memory on their servers. But the next highest choice they made here was that they're concerned about putting all their eggs in one basket. If they've got a very high level of VM density, what happens if they lose a whole server? Are they going to be able to restore those VMs fast enough? And we've got some technologies to address that in vSphere. After I don't know and other, the next choice was they're concerned about how long it takes to evacuate the VMs from a host that's running at high VM density. So if they need to bring that host down for a period of physical maintenance, is it going to take too long to vMotion all those VMs off of that host onto other hosts in your cluster? So we've also addressed that with some features in our new 4.1 release I want to talk about. So let me run down some features that are important to achieving good VM density that you should be looking for in a hypervisor. And as I mentioned earlier, memory is usually the limiting factor in what VM density you can achieve. So it's important to select a hypervisor that's got some sophisticated memory management techniques that let you oversubscribe memory. That is, the virtual machines have more memory allocated to them than you've got physically installed in the host. And it's also important to let you assign a minimum amount of essential memory to your critical virtual machines and ensure that those critical virtual machines get special priority treatment. And we support this with vSphere. If you're familiar with our memory resource controls, we have a setting in vSphere for each VM where you can choose a number of memory shares for a virtual machine. And you can assign more shares to your high-priority VMs. That will tell the ESX hypervisor that when memory becomes a stressed resource, give priority to these virtual machines with the higher number of memory shares. So that's what you would do for your critical workloads if you're sharing critical and non-critical virtual machines across a single host or cluster. Next, you want to make sure that those critical virtual machines have always available to them enough physical memory backing them up to support their memory working set. So you want to take a look and profile some of these critical virtual machines to understand what working set they'll typically reach when they're active doing work that meets their service level agreements. And you can set a memory reservation amount, which we recommend to be at least as high as the average working set for that virtual machine to make sure it's always got enough physical memory to keep up with its requirements. Now, after you've set virtual machine priorities and those memory reservations to set a floor amount of memory that your critical virtual machines will be given, you then want to make it possible to share the remaining memory across your other virtual machines. And we have some technologies built into vSphere to do this, to reclaim memory from virtual machines by the hypervisor and make it available to other virtual machines. Built into ESX, and it's been there from the beginning, is transparent page sharing. Transparent page sharing you can think of as deduplication from memory, similar to storage deduplication. And it works like this. If we've got 3 different virtual machines here running on our hypervisor, you can see here that we've got this green memory page that's in common to each of those 3 VMs. And we are storing just a single copy of that page in physical memory as managed by the hypervisor. Because it's identical across all the VMs, we don't need to store multiple copies. And that saves a significant amount of memory right off the bat. Now, should another virtual machine load a new memory page here, it's going to initially take physical memory as managed by the hypervisor. But what transparent page sharing does is it goes out and inspects the contents of that new memory page and hashes it, resulting in a hash value that ESX will look up in a hash table of shared pages that it maintains. And if it finds a match, in this case, that memory page hash value is A, we've already got a page with that same hash value stored. So ESX recognizes that it doesn't have to keep a unique copy of that memory page. It can share it with the same memory page that it already stored. So we've just freed up one memory page for use by other virtual machines. It's a very effective technology. Usually you've got virtual machines running similar operating systems, similar applications, and transparent page sharing can conserve a lot of memory in those cases. The next technology to look for memory conservation and reclaiming memory is ballooning. Ballooning works by borrowing memory from idle virtual machines to give it to busy virtual machines. And that decision of which virtual machines we do the borrowing from and the giving to can be driven by those memory shares that we set in the ESX memory resource settings. Ballooning works by putting a balloon driver in the guest operating system. This is part of the VMware tools that you install. And when the ESX hypervisor detects that memory is under stress and it needs to find some memory to reclaim from some of the guest OSs to support either virtual machines newly powering on or important VMs that need some more memory, it will communicate to the balloon drivers in the guest OSs, and the balloon driver will act as a process in that virtual machine that expands its request for memory. And the guest operating system will respond to that by making a decision which pages that it's managing in its what it sees as physical memory get allocated to that balloon driver process. And that's the beauty of memory ballooning. We are not trying to guess from outside the virtual machine which memory pages to give to the balloon driver. We're letting the guest operating system do it. And it has the understanding of which processes it's managing are more important than others. So it will typically give processes that are at lower priority and give their memory to the balloon driver, which will then pin that memory once it's given those memory pages so that the guest OS cannot go and claim them again. And the balloon driver then communicates with the ESX hypervisor to tell it, okay, these memory pages have been pinned by the balloon driver. It's safe to go grab those memory pages and reclaim them for other virtual machines. So ballooning actually results in the greatest amount of memory reclamation as managed by ESX. Now, sometimes ballooning and transparent page sharing aren't enough when memory really gets under stress, and then you need a fallback method. And for that, we do hypervisor level swapping. So when memory can't be reclaimed fast enough using ballooning, which is a common case because that ballooning process takes time, we have to wait for the guest operating systems to make those decisions on which memory to give to the balloon driver and which pages to swap out at the guest level. We sometimes have to respond faster, and we do that by having the ESX hypervisor select memory pages that it's managing and swap them to disk. And that immediately frees up additional memory for use by other virtual machines. Now, the problem with swapping to disk is it's slow. Disk is 1,000 times or so slower than memory accesses. So you want to do this as little as possible. So we make it our last resort method of reclaiming memory. But we've added to ESX 4.1 a new technology called memory compression that reduces the penalty of this hypervisor swapping. Memory compression works by designating a region of memory we call the compression cache, and ESX will attempt to compress memory pages, and if it can do so, it can sometimes store 2 memory pages in a single page in its compression cache. So you can see that operation of compressing those 2 pages A and B, which is done with a operation like a zip compression, allowed them to take just 1 page in the memory cache, freeing up 2 pages in the physical memory managed by ESX. So we've got a net 1-page benefit from doing this operation. And if we do have to go and retrieve those memory pages from the compression cache, that decompression operation is hundreds of times faster than retrieving a page from slow disk. So we're avoiding the slow disk read-write operations, but still giving us that buffer of hypervisor level swapping that's important to back up the other memory management techniques we have in ESX. Another aspect to look for in a hypervisor to achieve high VM density is we don't want to introduce any complexities, making you manage virtual machines differently than physical machines because of some strange properties in the way that they manage and assign memory. And we've seen that in some of our competitors' approaches to memory management that in the case of Microsoft's beta release of Hyper-V that they're expecting to ship in 2011, they've got a feature they call dynamic memory, and it works primarily by starting out with a small physical reservation of memory in a virtual machine and then hot adding memory as its needs increase. The problem with that is, as we've seen with some simple software installers, in this case trying to install Microsoft System Center, is that the software installer, as soon as it starts running in that virtual machine, detects that it doesn't have enough memory to support the installation of this product. That's because the virtual machine hasn't grown in its memory allocation when we started running this installer, and it fails right off the bat. So that approach of managing virtual machines differently than you'd see a physical machine managed tends to result in a lot of these negative interactions with software installers, with management tools, and so on that can't cope with varying amounts of memory that appear to be physically installed in these guest operating systems. We don't have that issue with the way ESX manages memory. Next aspect to look in memory management for good VM density is treat the memory in an entire pool or cluster as a shared resource. And of course, we do that with DRS. We use memory as one of the metrics that DRS uses to monitor a virtual machine to make a decision if it needs to be vMotion to another host to achieve its minimum allocation of resources. DRS lets us shuffle VMs across an entire pool, making sure that memory is not a resource we're shortchanging any VMs with the insurance policy of being able to balance workloads across a larger number of hosts. And then finally, you want to look for memory management methods that, like I said, don't introduce any complexities. You construct a virtual machine like you would build a physical machine, allocating a amount of physical memory to the VM. In our case, we can let you set absolute minimum reserved amounts of memory, give a virtual machine memory priority to make sure it's treated better if it's a more important VM. And then once you've made those settings, you don't have to touch that VM anymore. ESX and the features in vSphere will manage allocation of memory to that virtual machine automatically from that point. Now, if you're interested in this memory management technology, right after this session, TA8270-Get is a session being delivered by some of our engineers that is going to go into more detail on ESX memory management methods. I think it's in one of the other halls, not in Moscone West. Now I'd like to do a comparison between VM density features that we find in vSphere and ESX compared to some of the currently released competitive hypervisor products. I'm going to start with memory scalability, those technologies I just went through. As I mentioned, we've got 4 levels of memory management technology built into the ESX hypervisor. What we've seen with competing products is either no support for memory overcommit and none of these memory management techniques, which is the status of Microsoft's Hyper-V R2 product that's currently out in the market, or reliance on just a single method of memory management. Citrix Zen Server 5.6 is their first release that supports memory overcommit. It relies strictly on memory ballooning, which, as I described, can't respond fast enough to dynamically changing memory conditions unless it's backed by that hypervisor level swapping, which they don't do in Zen Server 5.6. And Jeff's comparison numbers from the VM density testing will show you the impact of that. Another product that we've looked at, Red Hat KVM, has a simple method of page sharing, and that's its only method of conserving memory. And that also seems to run out of steam far before the ESX results, which are based on those multiple levels of memory management technology. Resource fairness is another critical issue to look for in a hypervisor. You want to make sure that as resources come under pressure at high VM densities, certain VMs are not given resources preferentially at the expense of others. And we've put a lot of engineering effort into the ESX hypervisor to assure fairness across the virtual machines you have powered on. Of course, honoring those resource shares for CPU and memory and the priorities you've given with the memory reservations to those virtual machines. In other products that we've tested, we've seen some unfair treatment by the hypervisors. Well, where certain VMs, because maybe they were powered on earlier or reached a peak workload earlier, retain more resources at the expense of other VMs, and that's an undesirable situation. Next, you want to look for a hypervisor that's got good CPU scalability. So besides overcommitting memory, you're almost always going to be overcommitting CPUs with virtualization. That is, the number of virtual CPUs from all your powered-on VMs is going to be greater than the physical number of cores you have installed in your host systems. And we have a very efficient CPU scheduler built into ESX. We refer to it as a gang scheduler. And it accomplishes the task of scheduling multiple virtual CPUs across a finite number of cores. And that turns out to be a fairly difficult task to perform. We've engineered the gang scheduler in ESX to do it very effectively. So we cope very nicely with overcommitted CPUs. We also have very high virtual CPU limits, letting you go up to 512 virtual CPUs per host. The limits in other products are lower, and we've also seen, particularly in the Red Hat KVM product, their documents warning against overcommitting CPUs, and the performance and density test numbers that we've run back up that concern. Next, I/O scalability. If you've got I/O-intensive workloads doing a lot of network activity, storage activity, you want to make sure they don't run out of steam in the I/O area. And we've worked on building into ESX a unique driver model where we put our device drivers in the ESX hypervisor itself. We call that a direct driver model, as opposed to the approach taken by Hyper-V, Zen, and KVM, which uses generic Windows or Linux drivers running in their management OS. And we found that that approach, an indirect driver model approach, tends to bottleneck I/O in comparative testing that we've done. We also let you specify storage and network bandwidth that you want to allocate to particular VMs or particular workloads on those VMs with our new storage and network I/O control features in our 4.1 release that just came out. You want to look at VM density at a cluster level. You want to be able to scale up to a lot of VMs across a cluster. We support up to 32 node clusters with ESX, which is bigger than Microsoft's limit of 16. We support up to 3,000 VMs per cluster, which is also larger than the number of VMs that you can manage from those other products. And we also provide the benefit of logical resource pools, letting you divide a cluster into isolated pools where you can let business units work within their pool of resources and be assured that they're not going to impinge on other neighboring business units that have a pool on that same cluster. We very effectively lock the users out from stealing memory or CPU resources across pool boundaries. And none of the other products that we've looked at have that hierarchical or logical resource pool capability. Cloud-level scalability we are supporting, especially with the VMware vCloud Director product, which is backed up by vSphere. And vSphere's got very large limits in the number of virtual machines per virtual data center that it supports. We can go up to 10,000 virtual machines per virtual data center. You can triple that by using the linked mode available that links together up to 3 vCenter servers. And then I earlier mentioned the survey that showed customers were concerned about the evacuation time if they are running at high VM densities. We've addressed that with our 4.1 release, where we're now supporting up to 8 concurrent vMotion live migrations. Our previous limit was 4. You can now do up to 8 per any pair of host processors in an ESX cluster. And we've also speeded up the elapsed time required for vMotions by a factor of 5 with the 4.1 release. So that means if you've got 20 or 30 VMs running on a given host and you need to swap a power supply into that host, you can get all the VMs off that host and pushed onto other remaining cluster nodes much faster than with any of the other competing products that only support 1 concurrent live migration per pair of hosts. With those products, it's going to take you a long time to bring down that system waiting for all those live migrations to complete. Now, lastly, there's that all your eggs in one basket concern, and how do we address that with the features in vSphere compared to the competition? So we've got protections against guest OS failures, host OS failure, or host machine failure, and entire site outages. So if a guest operating system fails, we detect that with our HA feature that's part of vSphere to restart that VM on another host in the cluster. If we lose the whole host, HA will also restore those VMs on remaining cluster nodes. What's unique about vSphere, especially, is our FT feature for continuous availability for critical workloads. It's a feature that's not available from Microsoft or Red Hat with KVM. With Citrix, you need to introduce a non-integrated third-party tool that will let you do FT, but only on a very limited number of Windows operating systems. The nice thing about VMware's approach is we're OS independent. We don't care what OS or workload you're running in those VMs. For entire site outages, we fully automate the recovery process with our Site Recovery Manager feature. And other products either don't have that type of disaster recovery technology or it's not fully automated, which we found is very important in the case of a true disaster. So with all of these features listed here, you're going to have a platform that's very well equipped to deliver high VM densities and make those high VM densities manageable. So these are features you need to look for both today and in the future as the hardware stops becoming an issue, limiting VM density. It becomes more and more a management issue, and a lot of these features are related to management capabilities you need to get high VM densities. So I'm going to turn it over to Jeff now, and Jeff will take us home with the discussion of the VM density testing that we conducted at VMware.
Hi, I'm Jeff Bowles with Tenasia Group. Tenasia Group is an industry analyst firm that specializes in emerging and established technologies. And we examine these technologies to help understand how they function in the real world and apply to business problems so that you guys have a better assessment of what's out there in the wild and what works and what doesn't work. I'm going to start my session up here. You guys will get to see me dance back and forth between the stage and walking on the floor. I'm going to start my part of this pitch up here asking a couple of questions. Anybody in the room not virtualized yet? Yeah, I thought we'd see 0 hands. Who is not doing production workloads yet? Anybody here trying to figure out how to do production workloads? Anybody have SQL Server on their radar that they haven't virtualized yet and are interested in virtualizing? Well, it's actually fewer hands for some of those questions than I would have expected. Who's worried about the performance of their virtual infrastructure in the future as you continue to add workloads? So some interesting data points if you looked around at your peers there. Managing the performance of your virtual infrastructure continues to be a big concern. And my experience here at this VMworld, I've had so many performance-related questions. To see that many hands in this room is not at all surprising. It's been a constant theme underneath the covers of this VMworld. So I'm going to start with a little story here. Let me ask first, and I'm going to answer this question, so it's a rhetorical question. What's the importance of VM density? Is it just about cost? And you guys are probably in this room because you're VMware customers already. So is it important for you guys to understand cost of the competitive solutions? It might be if somebody is pushing you to introduce heterogeneous hypervisors. But VMware density, or VM density, workload density on your hypervisor is about much more than just upfront cost. It's also about the future of your data center. It's what you're going to be able to do with your infrastructure moving forward. And let me tell you a little story I'm going to simplify this concept a whole lot and talk about small numbers of workloads. Imagine if I asked for a show of hands about who's running 3 VMs on any hypervisor that I probably won't get any hands in this room. But let's say you have a hypervisor that you are running 3 workloads on today. You've tweaked and tuned this hypervisor, so it screams along with those 3 workloads. But you've picked another hypervisor. And maybe it runs those 3 workloads great. But it doesn't scale real good. It doesn't take additional workloads real good. It doesn't have a sustainable performance window. That's part of what VM density is about. So you go to add a 4th workload in that environment. It's because your application architecture has changed. You need one more web component or something in the future for this environment that you've tweaked and tuned. And because you chose a hypervisor that doesn't scale real well, your performance crumbles. It's not just sustained performance with 4 VMs, but when you add that 4th workload, because of the way the hypervisor time slices CPU resources, the way it virtualizes memory, your performance actually deteriorates when you add that 4th workload. We'll talk about this a little bit in the real world when I get to some of the charts up here. But say you lose 25% of your performance because you've added that 4th workload. Now you need another hypervisor. Now you need more licensing. Now you have more stuff to manage. Now scale this up and think about 20 workloads. Think about 30 workloads. It doesn't matter how big the hypervisor scales, but if it doesn't scale consistently across a wide range, give you a wide range of sustainable performance, you're going to be into a nightmare in the future when your hypervisors start proliferating, when you try to meet performance guarantees for your users. So I'm going to talk just a little bit off slide today and go through some of the charts. And my slides up here certainly aren't the pretty eye candy that Eric just finished showing you. But this type of stuff comes out in our testing up here that I'm going to talk about. So the testing we've done with VMware, we started a couple of years ago when VMware first started talking about this idea of a lower total cost of acquisition. That was right when competitive hypervisors were going free, and this seemed like a fairly ridiculous idea. You know, who would propose that VMware was cheaper when you had Zen out there running around free and Hyper-V being free? You know, this seemed kind of ridiculous on the surface. So we started digging in a little bit deeper, and first we went through some of the cost case for a cheaper hypervisor cost of acquisition. Went through the licensing models that VMware had dug into, and we kind of validated those numbers to see that they had good licensing metrics, all this type of stuff, and that the model held water. And once we got to that point, we said, yeah, sure, this looks good on paper. Now let's see, is there really a difference between hypervisors? Because at the bottom of those calculations, the case was very much built on VM density. How many workloads can you put on a single hypervisor? So we put some things through the lab at that time. And at the time, in fact, Eric may have to hold me accountable because this is a couple years ago now. It was Hyper-V and ESX at the time, right? And the metrics, the ability of those hypervisors to virtualize workloads were significantly different. In fact, there was consistently at least a 25% performance gap at any number of workloads that they could virtualize the same number of VMs at. But when you started scaling, like ESX would take at least twice as many workloads as Hyper-V. And frankly, we stopped with twice because we were bored. We didn't want to keep adding workloads to take it out further. Twice as many workloads got to be kind of ridiculous, right? So the case was clearly made in VMware's favor at the time. So since then, we've been updating those tests maybe every 6 months or so, really with the release of next-gen hypervisors. Every time somebody releases a new version, introduces a new feature. And that's also given us the freedom to go through a couple of iterations of different test suites. Now, we've been doing this for about 2 years. We used a number of different benchmarks. We started out with DB Hammer, which was a SQL Server benchmark. Ran SpecJBB as well, which was a Java virtual machine-based benchmark, which tortures memory fairly heavily. And most recently, we've turned to DVD Store. DVD Store was initially authored out of Dell. A couple of guys over there put together to simulate a real live in the wild DVD Store web app. Somebody selling DVDs. So, client server emulation. You run a SQL Server base that's the back end behind this web store, and tweak and tune a whole bunch of stuff to simulate web servers attached to that database, and then clients hitting those web applications on those web servers. So lots of scripts automate all this. But one of the nice things about DVD Store is you get quite a bit of variability between runs, too. So you can run it a bunch and get some randomness injected. It's not real easy to cache or optimize stuff around. So you get kind of real-world results. For a few of you guys in the room, some of this might be pretty interesting because consistently on the performance front, when we get to the charts here, one of the things I've heard over and over again here is the challenges of proactively planning to sustain performance in your environment and understanding what workloads you're going to do in your environment. So more and more today, the best approach to tackling some of those concerns is proactive upfront testing. So you can look at some of these test results up here, get an idea of what kind of performance we were able to extract from a single environment based on the environment we're using, and maybe think about reusing some of these benchmarks that we've used to date. You can also go back through the old historical reports, look at some of those things on other hardware, to see if some of these things will suit your needs on getting a proactive stance on what your environment's going to do as you add more workloads. But anyway, back to DVD Store. This was a fairly randomized workload. And we applied DVD Store to the latest gen of pretty much the full market of the hypervisors. The only thing missing was Oracle VM, which wasn't quite ready for prime time when we were doing this, and still isn't as I understand it. But we did Zen this time around, Red Hat KVM, and Hyper-V R2. And this was with the 4.1 release VSXi. And one of the things that we wanted to test was some of the new memory technologies in these competitive hypervisors. Zen had added dynamic memory control, DMC, which was a memory oversubscription technique. Red Hat KVM had kernel same-page merging in it, which is loosely the equivalent of transparent page sharing inside ESX. Repoints the same memory blocks to single copies. But at the time of testing, Hyper-V still hadn't added much of anything else. So we ran this using the light workload set up inside DVD Store first. And the way the DVD Store benchmark was set up is that we ran each VM as a SQL Server database using 1 gigabyte databases. Now, for many of you, that's not a very big database, but that stuff's all tunable on the back end, and you can scale to much larger databases if you prefer to see this benchmark under other circumstances. We started with the light workload profile, which gives the web clients a certain amount of think time, timing out on the web pages so people can read the simulated web pages and do order entry. And we ran this by starting a new SQL Server on a new VM and scaled it across many, many VMs until the hypervisor gave out and we couldn't run any more VMs on that single piece of hardware. So we used a ramp-up window also to let some of the memory page sharing techniques come into play. And I'm going to go through the specific charts and results here. And we're going to take a look at what happened underneath this light workload. The thing that surprised us was that some of these hypervisors performed pretty good underneath this light workload. Now, surely I couldn't be standing here telling you that everything kind of scaled the same. So there's probably a more interesting part to this story yet to come. And what I'll tell you is the light workloads ended up being a little bit of a case of lipstick on the pig. So this is the lipstick, and in just a minute we'll look at the pig. So I'll start off talking about the low end down here. We found about the same thing with Hyper-V. It tapped out at physical memory. We ran this benchmark on HP BL460C stuff with 8 cores in it, 24 gigabytes of memory, and the back-end storage were 10 Clarion CX4 120 disks, 15K stuff, RAID 5 LUN. So keep in mind that when you're looking at these numbers, if you're thinking about this as a model for anything that you're thinking about deploying internally, we're using 1 gigabyte databases on top of that Clarion LUN, and that CX4 120 has 16 gigabytes of memory in it. So that's at the top end up here. We're running about 32 gigabytes in a working set of data. So that's not all that far off from the 16 gigabytes of cache. So if you're using much bigger databases and trying to plan for storage off of this, don't do that. If you're using much bigger databases, do some testing yourself, because you're going to be outside of cache. You may be torturing your disks more than you thought you would. So just a word to the wise there. But anyway, in keeping with past results, Hyper-V tapped out with the physical memory in the box at about 24 gig. You have to have a little for the core OS. And you can run the VMs right up to the limit of physical memory because there's no oversubscription. And they still demonstrated good performance. They marched about in lockstep with everybody else here. And one of the interesting things to observe is that Red Hat did pretty good here with KVM. Close? Yep. So they managed to get 6 more gigabytes of memory by using kernel same page merging. That's a little bit of a testament to what you probably get out of transparent page sharing as well. So to be able to squeeze 6 gigabytes more into 24 gig, that's 25% more. But the lipstick part was that Zen server marching lockstep right up here to 32. And how could that be? So what we did was we amped the benchmark a little bit from there. So amped up the workloads. We removed the client timeouts. So there were no client think times, no client wait times inside the app. We added another thread which simulated another web server attaching to the back-end database. And things were pretty aggressive there. And that's where the pig came out and the real differences between hypervisors showed up. And you'll see that there's a distinct delta between the performance of these different hypervisors. And there's a huge window up here where ESX is pretty high above all the competition, right? Another thing to note is that there's a huge area over here where ESX ramps earlier than the rest of the competition. So if you run a small number of VMs, you might get more performance out of your hypervisor even sooner with ESX. If you run a large number of hypervisors, you'll get performance out of ESX a lot longer than other hypervisors are able to do. So, looking at Zen server and the difference here, the thing that came to the surface is that Zen's dynamic memory control is not very sophisticated. And you have to keep in mind the maturity and the sophistication of all these features as you see them coming out in competitive hypervisors, because we continue to find that they're not quite fully baked yet. So, stay in touch with this series of reports. It's on the front page of the Tenasia Group website right now. We'll be up on VMware more than likely soon. Until these things get fully baked, there's going to remain a big performance delta. What happens with Zen is that they're using an unintelligent flat reallocation mechanism for physical memory in the box. So let's take a hypothetical here. One workload, if you have one virtualized workload running on top of a Zen hypervisor, configure for 4 gig of memory, 4 gigabytes of memory in the box, and get all that memory. Now, this is hypothetical, so I'm not dealing with the memory that would have to be reserved for DOM0, the host operating system. Let's just use the hypothetical here. That's a little bit simpler. So 4 gig or for that one VM. If you add another VM configured exactly the same way with 4 gigabytes, well, the first one loses half its memory, goes to swap. Second one gets half the memory you've asked for, with the other half going to swap. And it's flat across the board. There's really no mechanism in place to respect workload pressure. There's no same page merging whatsoever, so there's no transparent page sharing. So that's the same model that's used, and it's used at the time the workload is provisioned. It's used whether you're going from 24 to 25 workloads, going from 1 to 2, 12 to 24, what have you. So the problem is that oversubscribing memory, swapping out memory, oversubscribing to the point that you have to swap, is the hardest thing you can do with a hypervisor. Performance just starts to tank because you're introducing I/O wait time for every processor instruction that you want to execute now that has to go to that swap memory. If you can't be really intelligent and elegant about how you're handling memory oversubscription, and you just flatly impose swapping on everybody, you're going to see performance tank. So until Zen starts to mature that mechanism further, I don't expect to see this improve at all. What happened was that with scalability, this performance gap between Zen and ESX really gets bigger. This is a scattergram because there's quite a bit of variability between individual runs. You can see some of these marks hopping around up here. But the trend over time, if you draw an average trend line through each one of these represents the delta at a specific run between ESX and Zen. If you draw a trend line through all those points, you can see that down here at one workload, it's only a 35% performance gap, and up here at 22 workloads, there's a huge above 55% performance gap. So this report, in more detail, all the details behind it, is available on the Tenasia Group website. Just go to the front page, you'll see it in the free sample report section. But for those of you who we haven't run too far over time here, I'm going to add one last element to this discussion to emphasize why VMware density, why VM density, workload density, is important to your infrastructure. Say someday you've moved into a service level arrangement in your infrastructure. The way that we consume IT resources across our organization is changing, is at least poised to change, and I expect it will change significantly in the future. You may have an app dev group that you eventually do business with someday based on the workload capabilities of a piece of infrastructure you're going to provision. Say app dev group comes to you and says, hey, I need 25,000 ops. I need 25,000 of something, or I need whatever number. With ESX here, you can say, hey, I know if they're running 4 workloads, they're going to get it. Whatever 4 workloads they have, my infrastructure has the potential to deliver to that service level for those app dev guys. If they want to change their application architecture and add 5 more servers, I know I can still get it up here at 9. If they scale out to 21 and get that, they can build whatever application architecture they want and know that I've allocated, based on cost maybe, some level of performance and resources to them. I have this wide window of stuff that they can do with those resources. Say you're running some other hypervisor, Hyper-V, for instance, and they ask for the same thing. Well, how many servers are you going to use? Well, I'm going to use 5 servers for my application architecture. Oh, well, I can't give you this with Hyper-V because at 5, I can only deliver this much performance. Oh, I guess I'll have to give you 2 hypervisors, 2 physical servers to support your needs. Well, say that same group maybe had 8 workloads, so okay, I can do that at 8. Say in a year the application architecture changes, and they want to add 3 servers to the application architecture, 4 servers to the application architecture. Uh-oh, my performance has dropped. I can't meet that service level metric anymore. I have to give you another server. That's the importance of VM density outside of just cost. It's the capabilities of your infrastructure to sustain performance as things change and deliver you IT service. At the end of the day, what we found is there's still a big difference between hypervisors. 1.7 to 1 to 3 to 1 density ratio in favor of ESXi today. And based on our assessment of those cost models a couple of years ago, we decided at that time that just a 1.5 to 1 difference could give you a 29% upfront cost. The cost to the future of your virtual infrastructure is likely much greater than that. The cost today is more than 29% just in upfront. That's it. So if you guys have additional questions, I also have an Ask the Expert session on performance, just right over here at the end of the Moscone West floor by the windows. What's that? Yeah. You bet. At 1:30 today, all the way at the other side, so by the windows over there. So.